Well, here we go. We're now in the last unit of the semester. Thank goodness, huh? What a strange semester this has been. I feel like I'm talking, radio-free Europe. I'm captured now for the last 200 years, and I'm trying to get out some messages to you guys. I guess it's not that, though, right? So we spent time talking about, the how stars are born and what the nature of a star is with, looking at the structure of our sun. We really couched it all in terms of how does energy get formed and how does energy move through a star, and what is that energy process called the proton-proton chain. And so what we find then is that for the most of the life of a star is a main sequence star, where recall, if we look at the HR diagram, where this is the temperature of the surface of a star, and this is getting hotter in that direction on that axis. This is the brightness of a star, and it's getting brighter going upward. That most stars fall within a very narrow region called the main sequence. And so basically 90 to 95% of all stars fall within that very narrow region called the main sequence. And basically what we said within the main sequence is that these are just normal stars producing energy based upon the proton-proton chain. Now, larger stars have a slightly different process than what we went through in class, which was for a more smaller, medium-sized star with proton-proton chain than I went through with that. But the essence of all these processes is that 4 protons or 4 hydrogen atoms through fusion, which is the process where small atoms combine in a nuclear manner to form a heavier nucleus or a heavier atom. And so 4 protons form together in a nuclear process to build 1 helium atom. And again, for most of the life of a star, the process that you see there within that star is within the main sequence. So if I asked you on an exam, I think I did, where does the star remain primarily on this diagram named after Hertzsprung and Russell, the HR diagram? So again, this is the HR diagram. What does it say? They are main sequence stars. Main sequence stars. And they'll remain there until, frankly, one thing happens. And that is the loss of fuel. So what will signal the death of a star? The death of a star comes from one reason: loss of fuel. And what's that fuel? And we just said it, hydrogen. Because remember, in this process of the proton-proton chain, hydrogen gets locked up into helium. And helium, though it's it's very similar on very close to the simplest atom, which is hydrogen, is still not hydrogen. And so it's not a fuel in this process when the star is along that main sequence. But time goes on. So, if I look at our PowerPoint, it starts out with a nice picture of the Cat's-Eye Nebula. Looks really neat, doesn't it? And we'll talk about what this is. It's really what's going to eventually be similar to what happened to our sun as it gets close to its death, or to its death. But let's go the other direction. When a star like the sun and other stars are first born, then generally what we find from the center of the star all the way out to the edge of the star, the composition is the same. What we see is that there is a large amount of hydrogen throughout, and there's secondarily quite a bit of helium. Nowhere close to what hydrogen is, though. Now, probably right up the top there would just be a little tiny layer of metals for population 1 or 2 stars too. But these are the primary stars. So what happens? As time goes on, the hydrogen gets locked up into helium. And so about the age of where our sun is, if you look at the center region, right from there to there is the core of the star, where all the fuel is being formed or used to form helium and energy and a few other particles. And so about half the age of a star like ours, about 5 billion years, about the age of our sun, we see that the concentration of helium is increasing dramatically within the core. Not so much on the outer part, though, is there? But there's still sufficient amount of hydrogen in the core that it's still performing as we expect it to perform. That is still is a normal main sequence star. But in the total lifespan, in about 5 more billion years, so much of the fuel of our sun, basically right through there, has been used up, and there's still some hydrogen in there, but it's a great deal less than what we had, and that signals the end of a star. So basically what we have here then is this. What we find is we have a region in the center that has a lot of helium. We have a region above that we'll find will begin to burn hydrogen. And above that is a non-burning shell, which is the majority of our sun, where that hydrogen is not useful to be a fuel. And to remember, to be useful, it means that it's basically producing energy by the proton-proton chain. So, what do we have then? This is a continual process of stars as they begin to die. As they begin to die, what happens is that the fuel is used up. Helium is not yet a fuel in a thermonuclear process. So the natural thing occurs. What occurs is that the energy processes of the core, so the energy of the core that streams out from the proton-proton chain reduces. So there's a reduction. And remember, there is this little battle going on between the inward crushing power of gravity trying to contract a star and the outward flow of energy streaming away from the core from the proton-proton chain. And so that was called hydrostatic equilibrium. So what happens here is this balance between the two forces. The hydrostatic equilibrium, fancy word, just means the balance between gravity pulling inward and energy flowing out is disturbed. What do I mean by that? What I mean is that gravity is larger. Than the energy flowing out. So the energy flow coming from the core. So it's kind of an interesting process that happens here. What happens here, as the energy is reduced, the core cools. Well, how can it not cool? Because right now the energy of that core is what's causing that energy to increase and to be greater and to be hot inside. So as we reduce that, the core has to cool down. And so all of a sudden, because it's cooling down, the gravity can start that inner region to contract. And remember what happened when a star was being born because of that contraction of that stellar cloud, that gas cloud that eventually would produce a star, as it collapses down, what we said was that gravity energy, really it's gravitational potential energy, like energy in a bank, is spent to cause that to flow downwards. It collapses and falls onto one another, and that kinetic energy is converted to thermal energy and it heats up. And so as the core cools, the core collapses, and because it collapses, the core begins to heat again. So isn't that kind of funny? What we find is that because the core is cooling, it will eventually heat up. And it all has to do with this balance between the forces within a star. So if I ask you on an exam, why does the core cool at the signal of its beginning death spiral? It's because the fuel is used up. So what's the results because the fuel is used up? Well, gravity can overcome the outward flowing energy. Okay? Well, what does that mean? That means then that gravity can collapse that star inner part down. Okay, I understand that. But remember, we go back to the story of star birth. If a cloud of gas is collapsing due to gravity, we have gravitational energy to use up, and eventually that causes it to heat up, which is how stars basically form until they reach that temperature of the core to be 10 million Kelvin, and then the fuel can be used in a thermonuclear process called the proton-proton chain. This is all Unit 2 stuff that we talked about. But because the core is heating up, the balance is disturbed. And so, again, because it's heating up, eventually it makes it hotter and hotter and hotter in a star. And so the star begins to increase in size. So the star swells up in size. And so what we see then is that the star has gone off the main sequence and begins to move up. And notice those diagonal dashed lines. Those relate to the size of whatever we're talking about, related to the size of the sun. And so this dying star actually swells up, as it says there, roughly 100 times larger than what the star was when it's a normal main sequence star. So it gets huge. So look at this. What happens is higher up on the HR diagram. Higher up, remember, means that it's brighter. But also it slides, so it goes up, it's brighter up, but it slides to the left. That means it's cooler than what it was. And there's a reason why. The outer side is so far away from the nuclear furnace, and it's so much bigger, the energy has more surface area to flow out, the surface cools. So I'll say it again. Because this dying star is so much bigger, it's now what's known as a red giant. And so up here, on the upper right-hand side of the HR diagram is the red giant and red supergiant branch spots right up in here. And because it's so much bigger, there's a lot more surface area for what energy is being formed in the core to flow away. So that reduces how much from every square meter. And it is farther away from the core, so it would normally just be cooler there anyway. So that's what we're seeing. So what occurs then? It gets hotter and hotter and hotter as it collapses. Remember what stopped the collapse of a star before. So this is just a little aside. What stopped? The collapse of a birthing stars. It's the energy flowing out from the core. And that just basically balanced, eventually as it settled down to be a main sequence star, it balanced out with the gravitational force. Okay. So what we see then, excuse me, I don't know if you're like me, I'm still just dying from allergies. This seems to be a horrible year. At least a horrible season for allergies, along with everything else that we're experiencing. So, you got this dying star. Down in this very center, the core is collapsing down. And that causes it to get hotter and hotter, and so basically what happens is this. I'm going to go ahead and erase a little bit here, up here. If I can look at this star, this dying star, right in the center of it is a helium core. And it's collapsing down, and from gravitational energy, it's getting hotter and hotter and hotter. And that's the size of the core, let's say, and let's say the star itself is way out here. Just showing a bit of it. So that's the core where all the energy is being formed. And as it collapses down, it gets hotter and hotter and hotter, and because it gets hotter, it heats up a spherical shell around that wasn't a part of the old core, but it gets above 10 million Kelvin. 10 million Kelvin was the temperature necessary for the proton-proton chain. So all of a sudden we have the proton-proton chain, and remember, the temperature max of a star like ours as a main sequence in the core was 15 million Kelvin. This is going to get much greater than that. So we have energy flowing out from here. We also have energy from the proton-proton chain and the new shell around the old core. Plus, of course, there's energy flowing out from here because, well, it's just so dang hot. And so that causes the star to grow and to swell up into this state. And it continues to do this. You know, the inner core collapses, getting hotter and hotter and hotter, heats up more and more of the surrounding shell to have more and more of it producing energy by hydrogen forming into helium, throwing out energy. And this continues as it is, and it's not a huge amount of time, thousands of years roughly, until finally what happens is the core hits an important temperature. And so what is the temperature of the core? The core hits 100 million Kelvin degrees. That's a huge temperature. And of course that means the shell that wasn't part of the core that's now above 10 million Kelvin can be very, very hot. It won't be 100 million because it's outside that old core. But it's still going to be dang hot. It's going to produce a huge amount of energy. Excuse me, and very quickly. That's why the star swells up. But this temperature is really important because at this temperature, helium becomes a fuel in a thermonuclear process. And so this is a new type of process. That's not the proton-proton chain. And so is this thermonuclear process now with helium that uses helium as a fuel is known as the triple alpha process. That's the Greek letter alpha. So that means alpha. Triple alpha process. So explain something. An alpha particle is simply the nucleus of helium. And so what we have then, we're not going to go into anywhere the depth in this process like we did with the proton-proton chain, suffice it to say that what we get is from these, we will get carbon plus energy. And that's really, limiting what this whole process is. But the whole point about this is it produces energy now, and it basically will produce eventually carbon as our primary ash that's left behind. Isn't that kind of weird? I mean, think about this. So we say that carbon was the ash from the triple alpha process. We say helium was the ash from the proton-proton chain. Now, right now, I think we need to be barbecuing, right? It seems to be the season. It's so nice outside. And so what happens when you have the barbecue going? Eventually you cook something, and then what's left in the little barbecuer cools down, and what's left behind is ash in that cooking process. So that's usually some carbonized, coal or piece of wood or something. We use the term ash for what's left behind as the major atomic element in these thermonuclear processes. It's the heavier atom formed from the lighter atom in this fusion process. So just to remind you, fusion is the nuclear process where lighter atoms, hydrogen, forms heavier atoms, helium, or helium forms carbon. And so it's just our terminology we use. And so, of course, why is carbon so important? I wish I could just ask you this directly. Where do we see carbon? It's the basis of life. And so carbon is, something we find in all life. And so we have this process. And so what we see then, when this occurs, what happens is that it had swollen up, and then it kind of reduces in size, and because it reduces in size, it gets a little dimmer, so it goes down, and it goes to the left because it gets hotter. And so we have this new process. But what happens in this is right when we hit this temperature, we get what is known as the helium flash. And this is where helium fuses furiously for a few moments. Really, when I say moments, I mean hours. The way I liken it is this, to give you an analogy. Imagine most of you sometime may have cooked with a gas stove. And so gas stoves, usually has a lighter, so you go over and turn on the gas stove, and you hear this click, 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 as a starter basically gets the gas burning, and then you set it to the temperature you want. But occasionally that gas doesn't light. And as you're sitting there trying to cook, you don't notice it for a moment, and then you look over and realize there's no flame, and you make the mistake of quickly turning on the lighter again of the gas stove to get it to light. And you neglected the idea that in those few moments it wasn't, lit and hot and burning. That gas collected. So then you hit this, it goes woof. All of a sudden you have no, hair on your hands. You might have lost your eyebrows. Hey, women, beard goes away. So not a good thing. So in some ways this kind of reminds me of that. All of a sudden it gets hot enough. There's a lot of helium in the core, and it just fuses that furiously into carbon and releases lots of energy. And then after a few hours of that flash, it burns down. And so now what happens is over time, just like we saw before, everything happens again. So it kind of repeats itself. So let me go ahead. So what occurs is over time, the carbon ash of this low mass star, so this is really talking about a star like our own, in a low mass star, like the sun, a carbon ash builds up right in the core. And in that new shell, remember, that got above 10 million Kelvin because it was heated by that collapsing inner core. It got above 10 million Kelvin, so it began to produce energy by the proton-proton chain. Well, it's producing helium, and it's a fuel. And it's producing more carbon also eventually. And what happens is it all repeats. As the carbon ash builds up, so as the carbon ash builds up, the core cools, the core collapses because of that gravity pulling it inward, overcoming the energy that's no longer flowing out as greatly. And again, the core heats up. And so what we get is what's known as a highly evolved low mass star. And let me show you an image of this. I'm going to go ahead and place this PowerPoint on Canvas today so you'll be able to see this more closely. So what you see is most of the stars, this non-burning envelope of gases, meaning not undergoing any thermonuclear reactions. Just like always, energy is just basically flowing out from it. Then what we find is right in the middle, we have a carbon ash. And it's collapsing down, getting hotter and hotter and hotter. Right above that, because it's so hot, it makes the area that used to be the shell that was producing helium from protons, it gets above 100 million, all of a sudden it's producing energy. And because it gets hotter, a new region above the original new shell actually gets hot enough to begin to form the proton-proton chain. So all of a sudden you have thermal energy coming from the collapse from gravity in the center. You have energy coming out of helium in the triple alpha process, and then a new shell above that in the old star envelope that's producing energy by the proton-proton chain. And that's what's known as a highly evolved low mass star. Now, what would happen? Well, if it was big enough and massive enough, the same thing would happen. It would just get hotter in the core, hotter and hotter and hotter as it collapses down from gravity. Energy just gets hotter. And if it got hot enough, then carbon could become a fuel. But there's a problem. Carbon, to be a fuel, requires roughly 600 million Kelvin degrees. But a low mass star has only so much money in the bank, so to speak, in gravity energy. So a low mass star doesn't have enough energy to cause this collapsing down to stop. So it doesn't have enough energy to allow carbon to be a fuel. So what occurs? it just gets hotter and hotter. More and more energy flows out until eventually what happens, the outer energy is so much more greater than gravity, it just pushes that outer envelope of gases into space. So you can see that outer envelope is just shoved further and further and further away until finally it is shoved so far away it just kind of floats away from that core. And what that means is that it is effectively dead. It has killed the star. So let me go ahead and erase this. I'm going to make sure you have it one more moment. So what we get then is that the core basically pushes the outer envelope of gases, which is most of the gases of the star, out into space. And basically those outer gases just flow away, which basically kills the star. A low mass star. In some ways, what really happens, I'm going to go back to that original picture. I'm going to go back from where we started. If you see, it looks like there's different little envelopes coming out of there. Those are all those different little areas. So one scientist who studied these things, one astronomer, calls it like cosmic burps. Doesn't that sound pleasant? So as the star's getting close, it kind of burps out regions of gas into space, and they begin to swell out. Then it burps again, and then it swells out. Burps again and swells until the star is left as it is. And so what we get is something right here. This is where it's not so obvious. It looks like there was one burp and the whole outer shell is just expanding out into space. And right in the middle is that remaining core of the star, which is mainly, though not totally, carbon. And so how a star dies then, what's left behind is the outer envelope of gases swelling and moving through, and we call that a planetary nebula. Just a cloud of gas and dust swelling from the death of a low mass star, and it just spreads out into space and gets thinner and thinner over time. And of course, you know, what happens then is that those gases would eventually mingle with the interstellar medium and to be present in maybe the birth of some follow-on star ages later. Now understand, this little shell of gas right there has nothing to do with planets, excuse me. So it's really a misnomer, meaning that it's not related to the birth of our planets or whatever. There's another one. And so this is like looking through it. So it looks like it's thicker there, but it's really just looking through a thinner region straight on, looking through more gas at the end. It's more of a spherical shell of gas expanding out in space. Here you can see, obviously, multiple burps of gas into the region of space. Here is very, it's like there's burps, but they're very directed in two opposite directions, not so much spherical. But right in the middle of that region, you can see that white dot, which is very hot, And that core that's left behind, so the core that's left behind is known as a white dwarf. Now sometimes they call it a white dwarf star, but it's really not a star. It's the remnant left behind. So really, the white dwarf is what's known as the first stellar remnant left behind when a star dies. The gas is also that planetary nebula. So if I asked you on an exam, what's going to happen to the sun? It's going to die. Why will it die? It'll use up its fuel. What is the last fuel it can use? Helium. Carbon can't be used because the core cannot get hot enough. Just too low a mass, which means that the gravity bank, which depends upon the mass of a star, how much mass you have, kind of like how much dollars you have in the bank account, that energy, because of the low mass from gravity, is just too small to heat up the core enough to use carbon as a fuel. And so it's left behind with white dwarf. So it's primarily, though it has other atoms in it, it's made from carbon. It's very dense. A sugar cube size of material would be tons. So very, very dense. I wouldn't want to put that on you. It's called murder because it's so dense. And the reason why is as that core collapsed down, it gets denser and denser and denser. Kind of shoved everything together, compacted it. It's small, about Earth size. It's hot. It could be in the core of this thing, it could be hundreds of millions of degrees Kelvin. On the surface, it could be tens of thousands. And so it'll be very whitish blue looking. It'll be extremely bright, but there's a problem. What makes the thing bright? Brightness has to do with the luminosity and the size. How bright? Luminosity and size. Remember, luminosity is how much energy is flowing from a square meter of surface every second, and then the size. And remember, this was from Stefan Boltzmann law, depends on temperature of the surface to the fourth power. So this is very hot on the surface, so the luminosity would be very, very big, but it's so small, it's just not very bright. You can't see them without a telescope. So if I asked you, why is it that white dwarfs are so dim? They're small. They're just really small. So as a star dies then, what happens is as it gets hotter and hotter, it gets brighter because it gets so much bigger, and then as the gas begins to push away into space, planetary nebula is up here, and the white dwarf ends up down here on the lower left of the HR diagram. And remember, on the main sequence, on the lower part is the red dwarfs, middle is the yellow dwarfs, on the top are the blue giants. Those are main sequence stars, normal stars. This is a dying star, and right at point 11, right there, this star has died, And what's left behind? Has to do with basically the planetary nebula and the white dwarf. And again, why it's not a star is because it's not a thermonuclear process going on. Just very hot. What would happen with this thing over time, this white dwarf? Well, what happens to that briquette in your barbecue? What happens is after you get done cooking, it sits in the barbecue and it gets cooler and cooler and cooler until you have a cinder left. And that's what happens to most white dwarfs. They just basically cool over billions of years. It takes a long time for these to cool. So white dwarf cools to a black dwarf. Just a cinder in space, about the size of the Earth. Hey guys, I have a question for you. What do you get when you really crush carbon? You get diamonds. So do these basically black dwarfs have mountain-sized diamonds in them? Some have predicted that might be the case. But, you know, because it's so dense in the size of the Earth, if you try to be on a white dwarf or sit on a black dwarf, the cinder left behind after billions of years of cooling, the gravity would be so strong because the mass of this thing is still quite close to the mass of our sun. So the mass of this thing would be so tremendous in such a small region that the force of gravity would just squash you. You couldn't go there to visit. You'd have to have very specialized robots that could go to explore that, and they would have to be very, very tough because the gravity would be so tight. One last comment about this, and then I'll go ahead and stop this particular video, and that's this. So the fuel that we had for a low mass star. So the fuel of a low mass star, first off, is hydrogen, protons. Then helium. And remember, this required 10 million Kelvin. Helium became carbon. Excuse me, let me say it right. Helium has 2 protons and 2 neutrons. And then we tried to get carbon. And that has 6 protons. And each one of these produced a new fuel. So this produced helium, this produced carbon, and we never saw what that produced because it didn't happen. And again, remember, what did we say for the proton-proton chain? We said that the temperature had to be 10 million Kelvin because that's a measure of how fast these protons are moving. And with that high a temperature, it means that if they're going the right speed, they can get close enough, even though they're going to be slowed by the repulsive electric force between them, so that the strong nuclear force can grab on. To get 2 protons and 2 protons and 2 protons to come together takes a much higher temperature because they have to, the energy is really dependent upon how massive that is, that particle, because remember, temperature is a measure of the kinetic energy, and the kinetic energy is equal to 1/2 times the mass times the speed squared. So the mass of these of helium is greater than of hydrogen about 4 times, so it takes more energy to get them to go fast enough to get together to collapse together. And so now we get to carbon, we have 6 protons. It's going to take a much higher temperature to have the right speed because there's a lot more mass in a carbon atom. And so we can't get there. We can heat up to 100 million to get the triple alpha process, but we don't get hot enough for carbon. So one last thing. For a low mass star like ours, this can last, this fuel can last roughly 10 billion years. This is much less time. And so for every new fuel that comes along, write this down. For every new fuel that crops up in the process of a dying star, that new fuel is used up much more quickly. And the reason why is, well, because think about this. In the proton-proton chain, you're using 4 protons to make 1 helium. So that means you're locking up atoms within the core into bigger atoms, so there's less fuel. And because it's at higher temperatures, a lot of times that fuel can be used up much more quickly. So they just don't last as long. I'm not going to ask you how long each fuel is going to last. You look that stuff up. I'm not interested. What I do want you to understand is the amount of time a new fuel is usable is less time than the previous fuel. So hydrogen was the first fuel, used up at a certain amount of time. Helium was the second fuel, used up at a much less time. If carbon was able to be a fuel, it would be used up much sooner than helium, and on and on and on if we have more fuel, different types of fuel within a star crop up after each cycle of using up a fuel, cooling, collapsing, heating up, and then getting hot enough to get a new fuel to be activated. I hope that's clear. So where do we go from here? Well, we know of one stellar remnant, white dwarf. What about, for high mass stars? What is left behind with that? So we'll go ahead and use that to discuss the death of a high mass star in the next video. Take care, guys. I'll keep getting these posted up over the next couple of days. Have a good one, okay? See you. Bye-bye.